Yes, so I think the plan is I may have two talks that are both involve randomness, but they will be fairly different in flavor. So I hope that there will be something for anyone in any of the talks. So today's talk, before I start, let me say that this comes about as I follow the footsteps and picture of Michel Talagrand. As many of you know, Talagrand was awarded the Nobel Prize last year for his many contributions to probability theory, including monumental developments in the study of suprema stochastic processes. And today's talk will be various pieces and developments around some of his novel field tree in this area of suprema stochastic processes, but with very close connection to combinatorial phenomena around thresholds. And I have to say that since the earlier resolution of Talagrand's conjecture of selector processes and the Kalai conjecture, for me personally, I was very much inspired and encouraged by my personal communication with Talagrand to pursue this direction. So even though he may say that he is not explicitly active anymore, he's always very responsive and extremely passionate and driven about his problems. And if you get an email from him, might be very late at night, and he says, he just mentions a problem that he wants to see solved in one way or another before he dies. I think that pretty much got me convinced and driven to explore kind of the many mysterious phenomena that are around in his picture. And so I hope that today I could give you some good glimpse of what this is about. So let me first set up the general problem in such a way that later on we can develop this problem in either the combinatorial or the probabilistic route. So in this general problem, as our input, we are given a finite set X. And then on this set X, we are given a set of valuations lambda. So these are just valuations or weight functions that assigns to each element of X some non-negative value. And we will extend this valuation lambda just to be a linear valuation on subsets of X. So for a subset W of X, we will just define the valuation lambda of W as the sum over the elements of W of the value lambda. Okay? And I would usually denote lambda the collection of valuations that we have. So this is the set of all valuations that we consider. Now, the quantity that we are interested in is the following maxima. So let me denote it M lambda. And this is again a function that assigns a value to each subset of X. And M lambda of W is simply the maximum over all lambda in our collection of the value lambda of W. And for us, we want to understand this type of quantity under the interesting action of randomness. So in this case, let me denote XP. This is a random subset of X where each element is included independently with probability. And our goal is to study or to understand the behavior of this maxima M lambda of this random subset XP. Okay, so actually in computer science term, these lambda are really just the usual linear valuations. And then this maxima M lambda of W is what you would call an XOS, or fractionally subadditive valuation. So in that language, you are just trying to understand how does fractionally subadditive functions behave when you randomly sparsify the domain in which you are working with. Okay. If this optimization problem and the randomness is somewhat strange, let me now give you perhaps two motivations to look at this problem. And the first motivations will be from probabilistic combinatorics. So let me show you how this general problem would capture what we want to study when we talked about the study of thresholds. So, okay, so now let me give you the general problem that we look at in the study of threshold, and it will look as follow. So again, in the general problem here, we are given some ground set X, and on this ground set X, we are given a collection that I will call target structures. This is some hypergraph or collection script H that consists of subsets of X. Okay, and the question in the study of threshold is roughly the following. We want to understand whether this random subset XP typically contains some target structure H from this collection script H. So can phrase it more formally, but this is roughly the question that we try to answer in the study of threshold. Now, let me rephrase it in such a way that it will look exactly like the problem that we try to study here.
Contains means as a subset?
Yeah.
H is a subset of XP. Is that what you're asking?
Yeah. So we want to, yeah, so contains means a subset. So we are asking if XP contains as a subset some set H from this family of sets script H.
Triangle in a graph.
Right. Yeah. So not giving the specific examples here because I'm going in a slightly more general direction, but yeah, you can take specific instances. For example, if X is the collection of all pairs of vertices in a graph set of size n, XP will be a random graph, the usual Edish-Rényi random graph GNP. And then, for instance, usually our collection of target structure is the collection of all isomorphic copies of some graph, let's say a Hamiltonian cycle. And then this question becomes, does GNP typically contains a Hamiltonian cycle as a subgraph? Yeah. Okay. So now with the rephrasing, or actually let me set up one useful notation that we will use many times later. So let me denote bracket of script H. This is the collection of all subsets of X, W, such that W contains some H from script H as a subset.
It's a particular type of monotone Boolean.
Yes, and in fact, it is the general monotone Boolean function, right? So for every monotone Boolean function, we can represent it in this form, bracket H for some family H. There's a family of all of the minimal sets in this monotone property. Okay, so with that, let me now make the connection. So for every set H in our collection, let me denote, let me construct the following weight function, and it's the simplest one that you can imagine. So let me construct an associated weight, lambda, to the set H, and lambda will simply give the weight 1 over sine of H to every element that is contained in the set H. Okay, so in this case, we can check easily that XP satisfying this property, XP containing a set from H, or in other words, HP is contained in bracket of script H. This is equivalent to the condition that the maximum over H from this collection script H, lambda H of XP is equal to 1. But in fact, since it will be convenient for us later, let me also say that this is actually also equivalent to the condition that the maximum over the sets in the family of lambda H of XP, it just needs to be at least 1 minus, well, let me say here, 1 over L, where L is the maximum size of a set from our family. Okay, so as soon as the weight lambda H of this random subset XP is very large, very near to its maximum possible value, which is 1, then we will be able to conclude that XP lies in the desired monotone property bracket H. Okay? So in particular, we can think about the study of thresholds as kind of studying this maximization problem, but in the regime where we want the maximum under the sparsification to be really close to the maximum before we do the sparsification. Okay. And For the second motivation, which I will not be expand in too much detail, this is, but I want to mention this because this was the original motivation for Talagrand to pose the motivating questions. And these are some motivation comes from the study of suprema stochastic processes. And in this language, roughly, the random variables lambda of xp as lambda ranges over our collection big lambda, these are referred to as a selector process. And so in particular, the suprema of this process is exactly the quantity that we care about, the suprema m lambda of xp. And there's a major program of Talagrand.
What is the selector process?
Right, so what is a selector process? Well, I mean, this is the selector process. It is the selector process is exactly defined this way. So it's a collection of random variables indexed by these different valuations, and the value of the random variable corresponding to each valuation is exactly just lambda of xp. This is a selector process. And roughly what you can think of is this is a process that tells us the xp, these Bernoulli random variables tells us kind of which element is selected. So that's corresponding to its name. But one thing is that selector process is not some kind of weird specific stochastic processes. We can use the selector process to simulate very general stochastic processes, like general empirical processes. I don't want to go into details here unless people are interested, but yeah, so this is kind of why the most of the interest that we discuss here will be focused on selector processes, but anything that we do here generalized to much wider class of stochastic processes like empirical processes. So here we write Talagrand as a major program where you want to understand or obtain certain certain characterization in terms of geometry property, for instance, of suprema of general processes. And let me just say here also briefly, without telling you much detail, that with the advances in chaining, and this is not just the chaining from Talagrand's earlier work, but this also includes, for instance, the breakthrough on the Bernoulli conjecture of Bernoulli and Latala, studying general processes, which for instance includes empirical processes, or the centered version of the selector process. So instead of looking at lambda of xp, which you can think of as just a linear combination of independent Bernoulli p random variables, you can center these random variables. So instead of looking at the linear combinations of Bernoulli p, look at linear combinations of centered Bernoulli p. And that is called a centered Bernoulli process, which is again an important process in this study. But all of these reduces to the case of positive selector processes. There's some caveats here, but let me summarize it in a somewhat non-precise sense this way. So in particular, this is why in its chapter on unfulfilled streams, many of the problems refer to positive selector processes. So kind of we understand chaining quite well after the resolution of the Bernoulli conjecture. So we understand how to study or take advantage of the cancellations in stochastic processes very well. But when we are reduced to the case of positive processes, there's absolutely no cancellation left. Then it's not clear what we can do to characterize the suprema of these type of stochastic processes. So yeah.
So the understanding above is mainly about getting the P, the value of P, where, transition happens, right?
That's right.
And in the second, there is more generally, I understand what
Yeah, so
other things.
in this general picture, really, so first you can think about this question one as understanding for which value of P can we guarantee that m lambda of xp is very close to 1. And in this picture, we are asking for which value of P, essentially, we will see in just a second how to reduce it to this phrasing of the question. Would this value m lambda of xp be large? Large may not be very close to 1. It may be an absolute constant, maybe 1/2. Yes. So that's the relation between the two settings.
Can you say something more? What you said last part with the Bernoulli conjecture, it's not familiar to me, so.
Okay. Yes, I can say a little bit more about that. Though we will not go into much further detail in this direction later on. So, for instance, well, you can write down general empirical processes. So, let me think, should I go with empirical or centered Bernoulli? Let me go with the centered Bernoulli processes. It may still look to you a little bit specific, but let me say that everything generalized to much more empirical, much more general ones like the empirical processes. So what is a centered Bernoulli process? It is a process where you are given again a collection of valuations or just vectors of weight lambda, and now you look at the random variables. Now instead of lambda of xp as we looked at before, we look at the random variable z lambda, which is a sum over the elements x in our graph set, lambda of x. And then here we look at the centered version of the Bernoulli P, which is Bernoulli P minus P. And well, in a sense, for instance, if we maybe replace this by a Gaussian, maybe you can normalize the variance to make them match. But if you replace this by a Gaussian, then literally all of these random variables z lambda that we look at will form a Gaussian process. And now there is a characterization of the suprema of the Gaussian process, and this is in terms of the appropriate metric geometry of certain metric space that you construct corresponding to these vectors lambda. Okay, of the L2 metric space of the lambda and various metric properties of the space would dictate what is the expected value of the suprema, maximum over lambda of Z lambda. Now, in the Bernoulli case, the situation will be a little bit more complicated. So already there will be kind of different geometries at play in terms of this lambda. There will be the L2 and there will be the L infinity, L1 geometry. But beyond these pieces, beyond the geometric pieces, what has been shown with the resolution of the Bernoulli conjecture, so that is the advances in training, is that roughly the suprema of these type of processes is dictated by different informations. So some of them comes from different geometries associated to the weight vector lambda. And there's the last piece in this picture, which is just the suprema of a process where all of the weights are non-negative and all of these centered Bernoullis becomes just the usual non-negative Bernoulli. So in that last piece, we don't have yet any geometric characterization of what the suprema should look like. And that's kind of why we focus only on that case in this talk. That's a very high level description of what happened. Yeah. Okay. All right. So with that, let me now go into the next part, where I will tell you now what is exactly Talagrand Selector's process conjecture and how it relates to any of the motivations that we have discussed before. So we see that this conjecture is one that has many, many different formulations, and each formulation kind of tells us a different meaning or interpretation of the conjecture. Okay, so maybe we just say that the general high-level idea here is that roughly only under very naive obstruction, which we will now discuss, can this maxima m lambda of xp be small. So unless there's a very naive reason why m of lambda of xp is small. Usually it is not small. That's kind of the punchline. So to motivate the discussion of these obstructions, I will actually now go in the opposite direction of what I did here. So here I showed you that we can reduce the threshold problem to the study of these maxima. And now I will go in the opposite direction. So I will tell you how these maxima can be phrased in terms of an appropriate threshold problem. And then that will make the obstructions appear a little bit more transparently to us. So we start here with this definition. To define for each non-negative real number T, the family of sets H.
So far, this is a linear programming problem, right?
Yes.
Everything is linear in the.
Exactly.
You are looking for the optimum of some.
That's right.
objective one.
Right. So everything is about a linear program, then you randomly sparsify the elements. How does it behave? That's all that this talk is about. So, okay, for HT greater than or equal to 0, let me define this family of sets HT. This depends on the input to our problem, so the collections lambda, but allow me to later on we'll always fix the collection of valuations lambda that we look at. And so when I write HT later on, I may just ignore this bracket lambda. And what is HT of lambda? This is the collection of all subsets W of X such that this maximum M lambda of W is at least T. And in fact, you can think, for instance, that this is just the union over all the weights lambda in our collection of the sets W in X such that lambda of W is at least T.
So that's the monotone Boolean function in the usual way you do like.
Exactly.
Online.
Right. So, yeah, so I'm rephrasing now this maxima, this more analytic maxima in terms of monotone Boolean function or family of sets. And now I will study this collection of sets HT from a more combinatorial perspective. Okay. But know that, yeah, to define HT, there's no randomness involved, right? We just go over every single valuation lambda, and given the lambda, it's very easy for us to construct what are the W for which the valuation lambda W is at least T. Okay, so now there will be a description of obstructions, and these are really obstructions for XP to, one second. Should say first that of course now M lambda of XP being at least T, this is the same as the condition that XP contains some set H from this family HT, or in other words, XP is in this monotone Boolean function bracket HT. Okay. So now we rephrase this problem of understanding the maxima back to this question of understanding the threshold essentially so the question of whether this random set XP would lie in bracket of HT with reasonable probability. So now I can describe the obstructions. And these obstructions work in general, of course. So let me say for a moment, not restrict ourselves to HT, but let's look at the general family H of subsets of X. Okay, so given family subset H, what are the basic naive obstructions that tells us that a random set XP cannot lie in bracket H, so XP cannot contain some of the target sets from bracket H with reasonably high probability. And we know where to find these obstructions. So let me start here with what I will call the naive first moment obstruction. So in this case, this is just the simple union bound that we all know of. So if I tell you that the sum over all the sets in this family of P to the size of H is small, then directly by the union bound, we can conclude that the probability that XP is contained in bracket H will have to be small. Okay, so if we have this condition for H being this family HT, then immediately we get the conclusion that with probability at least 1/2, the maximum will have to be smaller than T. This is some control on the maximum M lambda of XP. But okay, I call this a naive first moment obstruction. So of course there is an honest version of the first moment obstruction, which is not much more complicated. So it's too low. Okay. Well, we can write it the other side maybe. So we have the honest first moment obstruction. Well, so in this case, I need to set up one terminology that's also quite useful for us later on. So given a family H subset of X, let me say that a family G, also subset of X, covers this family H if every set from H contains as a subset some set from G, or in other words, this is just the expanded form of the conclusion that H has to be contained inside bracket G. That's what it means for G to cover H. So kind of G fits inside, the set of G fits inside the set of H. Okay? And now if we do the union bound calculation, not over the sets in H, but over the sets in G, then we would obtain this conclusion that if the sum over all the sets in G, T to the size of G, is small, then we can also similarly as before conclude that the probability that XP is in H is small. Okay, so one more terminology based off this. Let me say that a family H is P small if this condition holds. So if there exists a cover G of H and this union bound proxy, the sum over G from this family G, P to the size of G, is smaller than 1.
If you do want to, since it's all formal in general, you give an example like the existence of triangle with an edge
Okay.
triangle.
Yes, so, right. So let's not maybe have the entire talk be just the phrase in terms of abstract things. So, right, so we saw here that there's a naive first moment obstruction and there's this first moment obstruction. In what cases do we really need to go and find for this cover? And kind of a good example to keep in mind is the situation where we look at the random graph. So let me do the setup carefully. So here, X will be the collection of all pairs of vertices on a graph set of size n. XP is the same as the usual Edish-Renyi random graph G and P. Let me set H as the collection of all copies among n vertices of this graph. So it's better to go with K4.
Yeah.
And you can add to it one tail or several tails. And if you do the naive first moment calculation, so if you want the sum P to the H for H in H to be small, then you will need P to be roughly bigger than n to the minus 5/7. But instead, if you now consider this collection G, which consists of all copies of K4 on n vertices, then clearly this collection G covers the collection H. And on the other hand, already for P of order n to the negative 2/3, you have that the sum of P to the size of G in this collection is smaller than 1/2. So if P is, sorry, I want P to be small, not big. So in conclusion, you can show that if you use this carefully chosen cover G instead of the family H, then we can extend significantly the range in which we have obstruction for G and P to contain a copy of this graph.
It will be tight in this case and in many cases.
Yes, and right, if this is a talk about threshold, then I will mention in great details that yes, and this n to the negative 2/3 is indeed the correct threshold, so we cannot push the obstruction any further. And we will very soon see when I state the Kalai conjecture that, of course, in general, we know that if none of these obstructions exist, then we get a very good prediction of the threshold. In this case, we'll get a prediction of the threshold up to a constant. Indeed, that's true. But okay, let me continue with stochastic processes for a moment, and we'll go back to these connections in a second. So, well, now we have some sense in which there are some basic obstructions that tells us that the suprema M cannot be very large, right? So in particular, this discussion so far tells us that if this family HT is P small, so if it admits a basic first moment obstruction, then the probability that the maxima m lambda of xp is bigger than t will have to be smaller than 1/2. So once these obstructions exist, we can conclude that the maxima cannot be very large, at least with reasonably high probability. So now let me state this amazing conjecture of Talagrand, which in this language say exactly the following. So this is Talagrand selector's process conjecture. This was iterated many times, but the first time was in 2006. And his conjecture says that actually this statement is roughly an equivalence. We know that if there is an obstruction, the suprema cannot be large, but if there isn't any obstruction, then the suprema has to be large. So if HT is not P small, then maybe I write it in this term first. The expected value of the maximum m lambda of xp will have to be at least ct. So here there exists a universal constant c, not depending on any parameter of the problem, such that the following holds. Okay, so this is sorry makes sense to everyone so far. I'm saying that the mention the proof, the conjecture later, but as we can see here, between these two claims, we have a very good understanding of what the suprema m lambda of xp looks like.
And you should say more that the linear programming duality would give you. It's a linear program, even before the not naive.
Right. There are many linear programs lying around. Maybe I'll get to
Okay,
that later.
yeah.
Yeah. There are actually different linear programs involved here. I don't know if I will be able to mention all of the linear programs, but okay, at least so far, just on this basic problem, this is kind of the complete picture of the prediction for what its behavior should be. And let me maybe say here that you can also, if you want to match between the two statements a little bit more closely, one is kind of a probability, one is the expectation. There's a kind of an easy translation, at least in this following sense. So the probability that m lambda of xp is at least ct for some universal constant c will have to be at least c. Okay, so of course not exactly kind of an equivalence that tells us exactly what happens when h is p small and when h is not p small, but conceptually these two make a pretty much complete story.
So this was made after the Kalai conjecture. The Talagrand conjecture was made after Talagrand.
So Talagrand selector process conjecture, I think it was independently made in 2006, and I think might be kind of before or after, but both the Kalai conjecture and Talagrand selector process conjecture originally, I think, appeared in 2006. Yeah, I think Kalai so mentioned in the paper that maybe after the paper was written, there was some discussion with Talagrand because it's small cover perspective. Talagrand also, I think, independently observing this as well. Yes. Okay, so what I will do now is tell you perhaps a whole variety of different lenses in which you can look at this statement. So many other equivalent reformulations of Talagrand selector process conjecture that may seem interesting from different perspectives.
Can you clarify? I'm trying to understand. So roughly speaking, what you're saying here is that if you want to understand the size, let's say the median of m lambda of xp, right?
Yeah.
It's the largest t such that ht is not p.
Exactly.
But
yes.
That's not a statement about lambda, right? We usually try to understand the behavior of these processes in terms of the set lambda. And I'm having trouble, translating.
So the thing is, HT is directly constructed out of lambda, right? So if you give me the collection lambda, I can write down the collection HT. Now the business is how can we verify that HT is P small or not P small? And of course, that's the big question here. But in principle, this collection HT is a deterministic collection that we write down just based on the deterministic information of lambda, and the value of the process or the median of the process that's dictated by the T for which this deterministic collection HT becomes not P small. So
it's kind of a dual, right? Because Mn is like the dual norm associated to the convex hull of the lattice, right? So
that's right. But yeah, here, yeah.
One of the big questions here is how could you say this is true, right? How can you use it? Like,
right.
For example, all of these chaining arguments, they're often useful in order to prove comparison theorems between different types of random processes. And here it's not so clear to me,
Sure. So yeah, I guess. Yeah, so I guess maybe Ramon is restricting myself just to the setup of selector processes and suprema selector processes. Here I want to say that, right, you still get a comparison theorem here, may not be in the cleanest form that you can apply, but the comparison is in some sense not directly on the family lambda, but you can do a comparison at the level of the underlying distribution that you are sampling this random set XP from. So here I'm looking at the product Bernoulli P distribution, and this is some characterization of what the suprema looks like for this product Bernoulli P distribution. Via this characterization under this conjecture, we can show that if you give me any other distribution, of subsets of X, Boolean vectors, with the property that all of the monotone marginals. So if you give me some other distribution, P tilde, this is some other random set, subset X tilde of X, and for any fixed set T in X, the probability that this random set X tilde contains T is at most the probability that the product Bernoulli P contains T, which is P to the T. Then you get a comparison. Then you can show that the suprema of the process determined by X tilde is dominated by the product Bernoulli P case. So yeah, so I want to say, right.
Do you have examples of this property?
There are some examples, and maybe I don't have exactly the source of this, but for instance, I know that people were interested in proving maybe sort of Chernoff type bound only under this type of monotone marginal condition. So I think it appears maybe somewhere in computer science. I don't know exactly the application right now, but I think we can discuss that later. Yeah.
But just, I'm trying to parse it in real time, right? This is a stronger property than the property that lambda of xp, the distribution of lambda of xp for each individual lambda is comparable, right? This is a much stronger property.
That is correct. Yeah. So here we are requiring this for any t, and in a sense, we need to require this for any t because maybe small subsets in the support of the lambda are responsible for the suprema. But kind of, yeah, this is maybe the extent to which I can guarantee you at this point, but we can discuss more afterwards.
Yeah, the question where I'm coming from is, there's if you have the Gaussian process, the
Yes.
characterization of the suprema of Gaussian process,
Yeah.
it tells you that the suprema of any sub-Gaussian process is
correct.
upper bounded by suprema of the Gaussian
Yeah.
process. Now, you would really like to have a similar theorem for Poisson process.
I
If
see.
you have a sub-Poissonian process, then is it true or is it false that the supremum of a sub-Poissonian process is upper bounded by a Poisson process? This could have all sorts of interesting applications. But it doesn't seem to be, this seems to be a much stronger assumption you're making here, if I'm reading it correctly.
Yeah. So, right. Maybe we can take the discussion much stronger. I think it's very interesting. But yeah, I guess here I'm just maybe writing the analog of what I want to be the analog of the sub-Gaussian tail condition in this more combinatorial case. And I think this is probably like somehow the correct sub-Gaussian analog. But maybe when we look at the specific application and we want to massage it and to understand what it exactly means in that case. Okay, we'll get there perhaps later. So, okay. I think I wanted to mention that as one of the comparison equivalent formulations of Talagrand's conjecture. Admittedly, in this combinatorial setting, the comparison is somewhat tricky, as we have just discussed. But let me mention some of the other interpretations of this conjecture. And the first one I want to mention because it was originally how Talagrand posed the conjecture. So this is equivalent to the selector process conjecture, and it says that if you look at the tail event, E, this is all the subsets W of X, such that the suprema M lambda of W is large compared to the average M lambda of XP. Then this collection of sets has to be P small. And here again, this big C is some universal constant, doesn't depend on anything in this problem. Okay, so maybe 1 second of interpretation of what this means. Well, of course, I write down here a tail event. So E is a tail event simply by Markov's inequality. You can show that the probability of this event E is small. It's at most 1 over C. But if I just tell you that the event E is small, that doesn't tell you so much about the structure of this event E. And what's interesting here is that Talagrand conjectures that E is not just an arbitrary event with small probability. It is small in a very explicit way. It is P small, which means we can certify the smallness of E by only using these very simple first moment obstructions. Okay, so somehow E is small and certifiable by the union bound, the point. And so here, Talagrand originally posed this conjecture because it was a direct analog of a characterization that he obtains in the case of Gaussian processes. But let me not maybe go too much into that direction. So far, I keep the discussion somewhat in the abstract world of stochastic processes. In this next statement, I will come much closer to the combinatorial interpretations, which will be what we stay with until the end of the talk. Okay, so this is a more combinatorial reformulation of Talagrand's selector process conjecture. What does it say? Here, forget about the process for a second. I just give you a collection H of subset of X, and the only assumption that we make is that this collection does not admit any first moment obstruction. So H is not P small. Now, an adversary comes in and give us arbitrary valuations lambda H. These are constrained to be supported on the set H. So it's a value that assigns to each element of H some non-negative number for each H from our collection. And let's make the normalization assumption that lambda H of H, or the sum of all of the weights given by lambda H, is equal to 1. Okay, so we start with this combinatorial information, just a bunch of sets inside our graph set X. Now some adversary comes in and can assign arbitrarily a total budget of 1 across the elements of each set H from our family. And the conclusion is that with probability some number C, we have that this maxima lambda H XP, where H ranges in our collection script H is at least C. And again, C is a universal constant.
So this should be duality in our program.
So,
From the conjecture above.
So, I want to say, not yet. There's no duality yet. Yeah.
Yeah, I don't see how the constants play, but
I can tell you the last formulation, which is from duality. Yeah, so here, roughly the formulation just comes from, so these lambdas are kind of inherited from the lambda that were underlying the process that we considered before. This family H, you kind of carefully consider, and it's some analog of HT. And somehow just putting in this language, you can forget about T, forget about HT and the stochastic process. We just have this much more combinatorial problem, and we get this combinatorial information. Okay, last formulation maybe, because we are kind of hinting at some sort of duality in this picture. So in this last formulation of the conjecture, I will put it in this form. Again, let's start with this combinatorial setting. So we have this collection of target structures H in size 2 to the X, and it is not T-small, which is a very usual setup for thresholds, as we will see in a second. Then we are given a family, curly W. This is also a family, a subset of X, and it has the property that it is a typical property under this Bernoulli P product measure. So in particular, the probability that XP is contained in curly W is at least 1 minus C for some small constant C. Then the conclusion is the following. There exist non-negative weights, alpha W, for each W in curly W, such that the sum of alpha is small. And on the other hand, the sum.
1 over C is small.
Yeah, so I'm thinking about C as a small constant. So here 1 over C is big. So it's small means it's bounded by some constant.
Yeah.
And on the other hand, if you take the alpha W combination of W, or really the indicator function of the set W, this dominates the indicator function of H for some H in this family, in the collection of target structure. So through duality, what is shown here is that roughly this conjecture is equivalent to the statement that if we have a collection of sets, which is not P-small, and any typical property in the product Bernoulli P measure, then really we can kind of take a bounded combination. So bounded here means the analog of, we can take the roughly the integral version of this statement, which is a big conjecture that Talagrand really wants to see solved, says that we can find some constant number of sets from this typical set W, for which the union of these constant number of sets already contains a target structure from H. We don't know that, but we know the conjecture here is a weakening of that, which says that we may not be able to find integrally a bounded number of sets whose union contain the target structure, but still we can find a fractional combination of the sets. The fraction here corresponds to the union of roughly at most a constant number of sets, and this fractional union dominates the indicator function of one of the target structures. And so this is one of the duality that's running behind the picture.
Do we know that the integral conjecture is not true?
We don't.
You
No,
don't.
I think I still conjecture, well, Talagrand still conjectures that it's true. Yeah, it's that the question that he wants to see solved one way or another before he dies. But that's a really interesting question. But right, so these are very different, perhaps, formulations of the selector process conjecture.
Would that question allow you to prove something that you can't prove using the fractional version?
Well, I don't want to speculate too much, but I think so. Yeah, I think that question would be very exciting. It's well, okay, I haven't even, okay, I will re-mention it in a second. We'll do more setups. Okay, any questions so far at least?
Yeah. There is some bound on tail event that comes just from monotonicity, like Borobash, right? I mean, you have a monotone Boolean function, it's some piece that achieves the probability half, then if you go a little up,
Yes.
just cos calculator, I give you something. So.
Yeah, so there's a Bolobash which says,
so how is this strong?
It is much stronger in a certain sense. I don't know if it targets the same sort of event. So I want to say that this is closely related to Kalai, which is understanding how the probability change, but not exactly at the transition point. Okay.
Are you talking about Bolobash-Thomas inequality?
Yeah, Bolobash-Thomas.
So
So just to say, I
actually-
mean, maybe if people don't know, I mean, if you take any monotone Boolean function and you look at with the P, which achieves the probability half, let's say, of being correct, you go a constant factor from this P, you take 100P, and the probability already decays exponentially.
But this inequality tells you nothing about which P achieves one half.
Yeah, exactly.
What he's trying to get here.
I know.
It's-
Okay. Oh, right.
Right, so this inequality is telling you for which P.
Which
get
P,
one.
yeah, very good, yeah.
Right.
That's a crucial difference
That's my question. And
Right,
you
but-
answered it.
but-
Very good, yeah.
Still, I guess I was going to say something along the line of we could imagine whether these kind of statements, which tell us really which P, maybe not so precisely, we expect the monotone property to happen with likely probability, can also tell us something about how the behavior change as we increase the parameter P by much. And I think if you targeting sharp threshold, I don't really know how to achieve that. But if you are looking at the Bolobash version where you allow yourself to increase by a constant factor, then I think you can do something, but not with certainty right now, to go from this type of characterization, which is strong enough to do something there. Okay. Speculation. Okay, so maybe the last remark I make is in this form of this conjecture right here. It looks very interesting, right? So if we look at a single term, lambda h of xp, of course, typically it has order around p. So without doing the maximization, without doing the optimization, every term here looks like it has order p, which can be very small. I'm thinking about p as being really an arbitrarily small parameter. And on the other hand, well, no matter how your lambdas are given, as long as the support of lambda, which is this family H, comes with this nice combinatorial condition, which is not p small, then it immediately guarantees that once you do the maximization, you can boost significantly the typical order, which is p, to an absolute constant c, which is much, much larger. Okay, so many different forms of the conjecture. We do know that this conjecture is true. I proved earlier with Jin Young Park. So the selector process conjecture is true. In particular, all of these equivalent formulations we can use. And right, we'll get back in a second, maybe towards Ramon's question. Of course, the missing piece here is, well, if you tell me, you give me a family lambda, you want me to tell you exactly what is the typical value of m lambda of xp. I give you this characterization, which is deterministic in a sense through this family ht, But I have to solve this algorithmic question of certifying that HT is not p-small or proving that HT is p-small. It's not exactly clear how to do that. And because of threshold reason in combinatorics, we very much wish to do this, even in very specific situations when it's not generally an easy task. Yeah, just to say that this gives us some very good understanding, but if we want to use this, then we still have to perhaps work quite hard to understand what happens in the specific problems that we care about. At this point, maybe I want to tie it back to a word that is more combinatorial, that at least allow us to see the phenomena in a somewhat more explicit way. And here I will write down the conjecture that is relevant to the setup of thresholds. And as we have already mentioned it, the Kalai conjecture, which is another amazing insight that comes from Jeff Kahn and Gil Kalai. Exposed in the same year, 2006. And given this formulation B of the selector process conjecture, you will see that the statement that I write here has quite strong parallel to that combinatorial version of the selector process conjecture. So let me start by exactly the same assumption. So let H into 2 to the X be not p-small. The conclusion here is simpler. Then you look at a random subset of X, not with probability P, but with probability P log X. And you can also replace this by log L, where L is the maximum size of a set from H. The probability that this contains one of the target structure will have to be large. Okay, so let me roughly describe what happens in between this statement here and this statement here as the following in the following picture. So let's think about this axis as telling us what sampling property or what level of sparsification that we are looking at. So we have Talagrand selector process conjecture, which tells us some phenomenon that happens when we look at sampling density P. Okay, we always fix behind this picture some family of sets H, which is not p-small. Well, so at this level P, what did we obtain? We obtained that this maximum lambda, m lambda of xp is at least constant fraction, is at least some universal constant c. Or in other words, this is telling us that a random set with density p is able to capture a constant fraction of the weight from some set in the target collection H. And this is strong in the sense that no matter how you assign a weight, this is always true. Okay, then we have the other regime where we can increase the sampling probability by a lot. So Cp log x. And here, once we have this log factor, then we can guarantee a lot more. For instance, we can guarantee that m lambda of xp is in fact at least 1 or equal to 1. Or in other words, xp already contains in full entirety a structure from this target collection H.
P log X, right?
P log x, yes.
Constant P log X.
Constant times P log x.
No, also in the M lambda.
Thank you. Yes, yes, yes.
Yes, this intuitively is what you expect. You just repeated this sample from your distribution.
Yes.
You get an integral.
And this is kind of intuitively what you expect. If this is what XP does, it gets a constant fraction of mass from some set from the family H. Let's say not from one, but from many of the sets in the family H in a very nice way. Then we can try to continue to iterate larger and larger constant fraction, more and more, like in every step we iterate a constant fraction. So in logarithmic number of steps, we'll be able to iterate everything. Of course, this intuition is not exactly correct because here we really don't have much control over which set H. We can iterate a constant fraction of the weight. But that high level connection is indeed correct. So indeed, well, in chronological order, there is a high level connection between these two settings, and we in fact first resolved the question in the setting of the selector process conjecture, which is much more challenging because of these general weights, but then kind of just extracting a piece from within this picture and then iterate on that piece, we can resolve in full the Kalai conjecture, which, as we discussed before, you can think about this setup as the uniform weight, but when you want the maxima to be really close to 1. So kind of you gain the simplicity from only needing to work with uniform weight, but you have to work hard. Well, in the end, it's not so hard, but you have to work in order to get this maximum to be very close to 1. Okay, so I would remark in just a little bit that, as Avi mentioned, at the level of XP, we won't be able to hope for a better result than this. This is tight. We need some constant here that is less than 1. We cannot guarantee that we get a weight that is very close to 1. But still, there's something unsatisfying here. We have here very good understanding of these 2 points at density P and density P log X. We kind of understand what happens below P, because then there starts to be obstructions. So once these simple obstructions come up, we know what happens. But what happens in between XP and XP log X? And mentioning this because from the perspective of the Kalai conjecture or the study of thresholds, we very much would like to understand better this very mysterious factor of log X. And at least maybe let's try to fill in this missing part in the middle of the 2 regimes.
You will talk about this, about the coupon collector, bottleneck and stuff, or you will not get it?
Yeah, so I will mention that in just a second when I mention one example. Yeah, I kind of...
Good example to give where you see the difference.
Right, yeah, I will write a general result that interpolates this entire regime. Then I will write an example showing why that's optimal, in particular why it's optimal here and also here. And we will see the coupon collector there. But yeah, I phrase the talk in a somewhat more general term. So I didn't just restrict myself to graph theoretic examples. In a random graph talk might be more friendly.
By the way, if you want to take a break.
I continue. If people are okay. All right. Allow me to continue.
Wait, sorry, could you pull down the board in the top left for just a second so I can see the one under it?
Thank you.
Yeah.
Okay.
If you don't need either, then you can move.
Well, yeah, okay. In a second, I will pull back for the picture. But... okay, now I use this board. Maybe.
There is never a reason to use this board.
Okay, yeah. Let me use this board. We only need to remember this version of the conjecture, the version B from this point. So let's temporarily forget about this original formulation. Okay. So this now is what I will refer to as a sharp version of the selected process conjecture. So this theorem says the following. So again, similar to B and similar to the Kalai conjecture, we have exactly the same setup. And let me even write here in the statement of the Kalai conjecture the following form that suggests more clearly the parallel. Now P small, consider lambda of H, which is just the uniform weight. Then the probability that this maxima is bigger than 1 minus 1 over L is at least 1/2. And again, L is the maximum size of a set from our target collection. Okay, so uniform weight, maximum very close to 1 with probability at least 1/2. Okay, now this is statement.
So that also this log X can be just logged up.
Yes.
Yeah.
Yes. And that's important for me. Thank you. So let H be not P small, in exact parallel with the two previous results. The conclusion, well, okay. Again, similar to here, some adversary comes in, and the adversary gives us arbitrary valuations, lambda h, that gives non-negative weight to the elements in H. And again, let's assume that the total weight is 1 for every set from our collection space H. The conclusion is that with probability, at least, let's say 1/2, you can make it anything you want. The maxima m lambda of not xp, but let's say xp and increased by some factor s. Think about s as an integer that's between, as a real number that's between 1 and log L. This is at least 1 minus exponential in negative s. Okay. So, of course, as a direct corollary now, while the selector process conjecture does not formally imply the Kalai conjecture, this statement does immediately imply the Kalai conjecture. Just take this parameter f to be a constant c times log L. You get here 1 minus 1 over 2 L, say, and then immediately once under the uniform weight, even without even needing for the general weight, once we have this to be larger than 1 minus 1 over L, we can conclude that xp times s already fully contains one of the target structure. Okay, so immediately imply the Kalai conjecture. In terms of selector processes, this statement is roughly a characterization of the large tail event. So if you look at this tail event E, that consists of all of the sets W, so that M of W is at least, well, not a big constant times the expectation, but at least 1 plus delta times the expectation. Then this event is an event with probability bounded away from 1, but we want to give a much more explicit structure on the smallness. And what we can say here is that this is Cp log 1 over delta small. So we do have to increase this P by log 1 over delta factor, but that is necessary, as I will remark in a minute. Okay, and the last thing is we remark that this trade-off, the trade-off is optimal. So this is really kind of the optimal, at least general picture. This is the general picture of a sublogarithmic x ps and what it captures. Okay. So let me now give you the example showing why this trade-off is optimal. Of course, that's going to be the same example that tells you why this log L factor in the Kalai conjecture is optimal, which is usually based on coupon collector type of behavior. So this is kind of.
But when you say it's optimal, you don't mean it's optimal. You mean it's there exists in that instance.
Yeah, that one I think.
I mean that, of course, yes, there exist some family H for which you cannot hope for better dependence than this.
So this theorem is not going to help you explain when the extra log in the Kalai conjecture
That's right.
does not, it's not needed.
That's right. So it doesn't at least directly help you explain when you don't need the log factor in the Kalai conjecture. At the end, in the epilogue, if I have time, I will tell you a little bit more about that. But the other thing is, well, still hopefully it gives you some understanding that might be very useful for going in that direction, because then you want to play first with a set that is in the sublogarithmic scale, and then you have to, of course, use some explicit information from the problem. That's not just in the generic setting. And perhaps once you have some, some foundations of the phenomenon here, then you can build off that with additional information to do something interesting. But okay, again, let me not go too much into that.
That is still a dream, or that is actually
That is, let's say that is still a dream, yes. Without too much discussion of what comes in the future right now. Right. Still, going back to the general setup, let's see what is optimal. So the optimal example is that I will take, there are many more that you can take, is the following one. So let me consider the ground set, which is kind of a rectangular board, many rows and R columns. And let me take this family H to be the family of sets H, which consists of exactly one element per row. Okay, you can show that if you take P to be something like 1 over R, then H is not P small. And on the other hand, okay, I need the weight just for this discussion, but I would just even use the uniform weight. Lambda H of X is just 1 over n times the indicator that X is in H. That's our collection of weights. And finally, let's make this use.
What are the rows and what are the columns? There are n rows.
Yeah, there are n rows, there are columns. And the set from the family H looks like this. And so one element per row. Yeah, and you can show that this is roughly 1 over R small, where R is the number of columns. This is not 1 over R small, where R is the number of columns. It is also some, if you change the constant in front of 1 over R, it will become constant over R small, but we won't need that right now. And I'll just set up the weights as the uniform weight, as usual.
You have a reason not to pick R equals n and look at perfect matching?
No, but
Let's
just write it in more general terms, but you can.
Yeah, okay, good. That's much more familiar to everybody.
I think. Okay, in a sense, the transversal is a simpler version of the perfect matching, right? Where we already see.
No, but familiarity is probably.
I see. Okay, let me. Yes. Okay, let me do that. Okay, let me say that you can just make this example work, just one sentence. So if we can now just observe that if we take a random subset of X with density P times S, then you can easily check that with high probability has at least this fraction 1 minus exponential in minus CS times n empty rows. And so of course, this implies, as how we set up the weights here, that m lambda of XPS is at most 1 minus exponential minus CS from potentially some different constant C. But of course, as Avi suggests, this example really persists in many different situations as long as we have kind of a coupon collector obstruction to the threshold. So for instance, I can now go back to the work that we are familiar with. So X is n choose 2. Again, this means XP is the arbitrary random graph G and P. This family H I can take to be some interesting spanning structure, but let's say that H is the collection of all perfect matchings on n vertices or Hamiltonian cycles. Again, you can check that this collection of perfect matching is not 1 over n small up to some constant here. And you can set up the weights just the same as we did all the time. So just the uniform weight on the edges in the perfect matching. Maybe now it's n over 2. And instead of empty rows, you can easily check that if you look at the additionally random graph with density P times S, and S is sublogarithmic, it will with high probability contains many isolated vertices.
The coupon collector is having degree 1.
Right. Yeah.
This one is everybody.
Right, so a coupon collector, as Ivy says, corresponds to this case, a necessary condition for having a perfect matching is to have degree at least one around every vertex. So any isolated vertex is an obstruction. And furthermore, here we can see what is the fraction of obstruction that we must have, which is exactly as we predict, 1 minus exponential in minus CS. Okay, so clarifies the situation to us. Okay. Right, so that's kind of the general discussion I wanted to say. So there's one application, right? So it feels like the fact that we can handle adversarial weights is very useful. We really wish to find good combinatorial applications of this general setup. There's one application that I can tell you now.
There's something I'm very confused about this formulation of the lambdas, because it feels that the lambdas, the weights play no role in this formulation, right? It's the set, the class H, which has to be P small.
Yeah.
Right? For example, you could take these lambdas so that they're only one on one vertex and zero on the rest, and now you're really talking about a different class of sets, right? So then you would expect completely different behavior from the process.
You can certainly, but
so it feels like.
Yeah,
so how can you get a sharp characterization when you don't take into account the structure of the lambda?
Well, you look at the worst lambda.
Yeah, so here we're looking at the worst
Make
lambda.
all the lambdas.
No, you cannot make all the lambdas.
But the support are separated, right? The support, we come with this condition that the supports of lambda cannot cluster on any specific location. So kind of the Peace-Bound condition tells us that the support of the lambda is lying kind of all around. And even now, if you come in and you want to say, okay, maybe you just concentrate all of your weights of lambda to the single elements here, to the single elements here and here and here, because of the kind of fracturing of the support, we'll always be able to say that even if you do that, if you effectively make the support of your lambda to be significantly smaller, still this behavior cannot be avoided.
The point is this direction. I mean, in the beginning you said you had both directions. One of them was trivial, the other one was not trivial. But in this formulation, the other direction is not going to be true, right?
Right, but roughly what happens is that so still if you go back to that statement where I claimed kind of a rough equivalence between the Peace-Mode and the not Peace-Mode setup, then kind of what happens is that there always exists kind of the worst possible lambda that you can put down in this statement here that would match it up with the other regime. Okay, that's my claim. So before, when we look at selector processes,
That I'm willing to buy, but if I give you just the general selector process with just the general set of lambdas, lambdas is given to you, you are not allowed to choose. Right?
yeah, that's
So
correct. That's correct. So, but these lambda h, they are constructed, they are not exactly the same as the lambda that you are given at the beginning. Okay, so these lambda h are constructed by looking at kind of the tail events in the selector process.
Come from this HT.
Exactly. So these lambda relate to the HT. That's why the condition is on HT. Otherwise, the support of lambda could have been everything, and there's nothing we can
So
do.
these lambdas have really very little relation with the original class lambda that you started from.
Exactly. Well, yeah, they relate through this collection of sets HT. Right. So yeah, and the worst lambda that you can construct it based on the HT, that's the lambda that will appear in this state.
So in fact, do you even need a statement for general lambdas? Would it be enough to just have it for uniform lambdas to deduce that statement about the HTs?
No, it's not. Yeah, we absolutely need the statement for general lambda.
You are going to give us an application of that.
I am going to give you an application where you need general lambda, but it's not in the direction that Ramon is asking about. But yeah, but you need to, you can't really just put uniform here on the set in HT. I kind of imagine that you take your lambda at the beginning. There's a set in HT that is kind of the set that you're interested in, and you just truncate the original lambda to that set. But the weights still vary inside this set, so you still have to capture that variation. But that's kind of hopefully explains a little bit of that history. So I mentioned an application. Okay, and I hope I have some time to tell you about the proof. I really wish to tell you about the proof. This application, I need a little bit of setup, but the setup, in fact, we are kind of familiar with from the study of thresholds. So far, of course, I have discussed these statements, and already even from the perspective of selector processes, or from the perspective of the Kalai conjecture, really the kind of condition that we wish to understand is this condition, that a family of sets is not p-small. How do we understand this, or how do we certify, prove things along the line of this condition in specific application? So just to set up the convenient terms to use, the expectation threshold, which was defined originally by Kahn and Kalai, this is exactly the P that we care about in these theorem statements, is PE of a family of sets H is the largest P such that H is P small. Or in other words, it is the smallest P such that H is not P small. So, of course, when we apply this theorem, then usually we would apply it with this parameter P being exactly the expectation threshold. And so the question becomes, how do we find the expectation PE when we are given some family of sets H, or even worse, when we are given the family of sets HT? And there are indeed open questions along that line, again, due to Talagrand, where what we wish to do is to understand in a more hands-on way the expectation threshold of the family HT.
I don't know if you just very strong message of this story, which you mentioned your theorem with Jin Young, but this Kalai conjecture was something, I don't know the Talagrand version, but the Kalai conjecture looks wrong to everybody, including them. They stated it.
That's correct.
Why should you believe that the first moment method should ever give you the right bound? It's such a naive method. But that's what it says.
Exactly.
So I think this message is something that
Yeah.
broadcast.
Right. So right. There's lots of stories to tell here, and this is a way to tell a story that I also very much like. Haven't quite gone in that direction, but really everything that has happened so far, either in the world of selector processes or in the setup of the Kalai conjecture, so in the setup of threshold, you could think of as just saying that the first moment is all you need. Okay, if the first moment tells you that something cannot happen, then clearly that cannot happen. But if you can prove that you cannot find any first moment argument to show that the collection of structures you can't have in a random set XP, then in fact up to a small change, XP roughly must already contain the structures that you want to find. So it's kind of,
A huge line of special cases of this were proved over the history of published combinatorics and experimental theory.
Right.
And this subsumes them all and
right.
many more. Yeah.
Yes. Yeah. So right. So going in the world of thresholds, it is interesting because the direction that we are interested in is usually the direction of showing that structures do exist in the random set, in the random graph, which is a direction that with the usual very simple first moment that we know we can never do. But now this statement tells us that we can also do it from the first moment perspective. We only need to show that there's no first moment obstruction to containment of what we want. Okay, and roughly the expectation threshold captures exactly the point at which we no longer have any first moment obstruction. All right, so maybe just to remind then, to remind you, the Kalai conjecture tells you that the probability that X at density C times the expectation threshold times log L or log X contains one of the desired structure from H. This is at least 1/2. And Talagrand's conjecture, for example, tells you that for P above the expectation threshold, no matter how you assign the weight, this maxima m lambda of xp will have to be at least some universal constant. And we also have this optimal version that allows you to go between the two regimes. Still, the question is, how do we determine the expectation threshold? And let me write the expectation threshold in this rather suggestive form. So P of H, we can equivalently write as the largest P such that the following, I call it ILP for integer linear program. This integer linear program has input the family of sets H, and it is the following program. So we want to minimize, sum over sets, subsets of X. We have as variables W of G, one for each subset of X. Here our objective function is the sum over WG P to the size of G. And the constraints here are that WG are either 0 or 1. And furthermore, for all sets from our family H, we have that the sum over G subset of H, W of G, is at least 1. This is just the condition for the cover in terms of ILP notation. And of course, what we want is that this guy, what we want is the largest P, so that H is P small. So it's the largest P for which this linear program still results in an optimal answer that's less than 1/2. Okay, so Talagrand, well, look at this program and he does the most natural move that you would expect. So Talagrand observed that you can take the natural fractional relaxation of this program, and let's define now PF of H as the quantity that comes up in this fractional relaxation. So it's a supremum over P such that now we look at the LP corresponding to H. It looks exactly the same as what we have before, sum of WG, P to the size of G. We want this to be less than 1/2. The only change is that W is allowed to take fractional value. And the cover constraint looks exactly the same. Okay, so by virtue of being a fractional relaxation, you can check easily that PF is always an upper bound to P. But the usefulness of looking at the fractional relaxation is that, well, we can pass now through LP duality. And in particular, if you just establish the dual variables, the dual certificate, that would give you a certificate of an upper bound on PF and hence also a certificate of an upper bound on PE, which is very useful because just by looking at this statement, it's not clear how we can certify an upper bound to this quantity PE of H. And that is very useful in applications, but not planning to go in that direction. So let me mention here yet another conjecture of Talagrand that somehow he conjectures that magically for this very wide class of integer linear programs, there's kind of no integrality gap. So conjecture that PF is at least PE, and it is also at most some universal constant times P. And really, this is a very general class of program. It's kind of program of a cover type. So the constraints are these cover type constraints. And that's pretty much the only characterization of these integer linear programs. But somehow, Talagrand believes that there's no integrality gap here. There's no gap between PE and PF. Yes.
And the interesting thing is where H contains large elements, because if they are constant size, then it's 2.
Exactly, yeah, so, and, okay, I'll remark on that in a second. Yeah. So let me rephrase this statement differently. So this tells us that if H has our cone W, which satisfy these constraints, a fractional cover. So if H has a fractional cover, such that the weight of this cover is small, then you can also find an integral cover of H such that this integral cover now is small, but with this slightly smaller parameter, p dividing by a constant. Okay, so roughly it tells us that we can kind of always round these fractional covers and we don't lose a lot in this parameter p. Yes.
Oh, no, the G is.
Yeah. Yeah, so yeah, it's right. When I look at integral cover. So let me say that just directly by using what we know from the Kalai conjecture. So of course, one of the earlier, I guess, motivation or one of the earlier reasons for fighting to prove this conjecture would be to establish the Kalai conjecture from its fractional version. But well, we do have the Kalai conjecture, and this conjecture we can think of it as kind of an interesting question on itself. Somehow, for this Y class of integer linear program, we can prove that there's no integrality gap. So, well, what do we know? We know that PF is at most PE up to a factor of log L, where again, L is a maximum size of a set from our family. Okay, and there are several different interesting works earlier on various different cases where we can get at the integral gap. So Talagrand proves that if you have a fractional cover, which is small and which is supported on singletons, so sets of size 1, then you can find an integral cover that is small with this parameter p over some constant c. And already in that case, the translation between the fractional and the integral cover is interesting. So the integral cover, in fact, must consist of fairly large sets, even though the fractional cover only uses singletons. And then it was extended later. This is a significantly harder work by Frankston, Kahn, Jeff Kahn, and Jin Young to the case where the fractional cover W is supported on sets of size 2. And there are various other cases that were considered. So Fisher and Person considered several ways in which we can rephrase this conjecture into other statements and also prove the equivalence for various classes of fractional covers. But in general, we are restricted to fairly specific instances if we want to achieve this constant integrality gap.
The fractional cover supported on one or two elements relation that it's 0 or.
Yeah, it's 0 for all sets of size larger than 2. Yeah. So as an application of our interpolation between the two regimes, we can prove the following. So if H has a fractional cover W supported on sets of size at most T, and W is small in the usual sense, then H has an integral cover G, which is T over log T small. Okay, so not exactly a constant gap as T grows, but well, given the sharp interpolation between the two regimes, we can pay here a factor of log T. Let me remark that even if you look at fractional covers supported on sets of size T, the family H, the uniformity L, of the family H that comes up can be arbitrarily large compared to T. So this is in general a much stronger conclusion than the statement that we have as a corollary of the Kalai conjecture where we pay a log L gap. But for instance, as another easy direct corollary of this statement, we can prove that the gap between the expectation threshold and its fractional relaxation is at most double log L. And this can combine this version right here with observation of Fisher and Person using just routing for sets in the fractional cover that have large uniformity, and mixing between these two regimes, we can achieve this gap of log L instead of log L.
So what's an example where it improves the bound we knew with some combinatorial, or you don't have any?
So
Some natural.
if you want an explicit combinatorial example.
Maybe, yeah, I don't know.
Yeah,
Something with, containing some structure that we are familiar with. I don't know, some graphs of some given degree or something like that, containing.
I think maybe I can't give you exactly one right now. And of course, we also expect that if you give me some example that we understand well enough, then we would have expected the constant gap from Talagrand's conjecture. So if we have our handle on the expectation threshold at all, it would probably tell us that the gap is constant. But yeah, it's good to consider. I think maybe you have to look at like somewhat complicated structure, but let me take that offline.
Yeah.
So, so don't have a lot of time left. There, I originally planned to sketch very briefly this proof. I won't now sketch it in much detail. I'll just tell you how the general weights becomes very useful for us in this setting. So roughly here, what we do is we set up these weights, lambda H for each set in H. And these weights looks like the following. So there's a normalization factor, and the weight lambda H as an element X, which is sum over all sets G inside H, the weight in the fractional cover of G, and we only count over the G that contains X. Okay, so if we normalize, this is the correct normalization.
Wait, what is he doing here? I'm a bit confused.
I'm giving a sketch of this proof.
Of that proof?
Yeah.
Assuming
the sharp version of the selector process conjecture, I'm giving a sketch of this proof. So that's why I'm setting up weights. Okay, so yeah, we can set up these weights. Now we just apply the sharp selector process result theorem with this lambda H. So we obtain that with high probability, roughly, if we look at this maxima, so if we maximize over H, right, the sum lambda H of X over the elements X that are contained in XP prime. So let me carefully choose this parameter P prime right here. So of course, let me say that we assume, for the sake of contradiction, that this family H is not CP over log T small. So this is our parameter P prime right here. And if we apply the sharp version of the selective process conjecture, then we obtain that if we look at the random set P prime log T, because H is not CP over log T small, this is going to be large. This is larger than, let's say, 1 minus 1 over 2T. Okay, and once you are given this, it's just a deterministic calculation to deduce that if you look over H and you sum here, all of the G in H, the fractional weight of G, together with the indicator that G completely lies inside xp prime log t, this will have to be large. Okay, so allow me to not do the explicit deterministic deduction between these two inequalities.
Just use the weights.
Yeah, so in this step, we use that the sets G have size at most T right here. But yeah, combine this statement together with the definition of the weight, we can write down this inequality. And now you can see how this contradicts our assumption. So the assumption will tell us that the expectation over the sum in all of the sets G in our fractional cover, even without the constraint that G lies inside H. W of G, indicator G inside H P prime log T. Let's see, P prime log T is less than P. So let me put here XP. This is, of course, just the sum over G, WG, P to the size of G, and this is small. So this is a quantity that should be small, even if we ignore this constraint that the sets have to come from H. And that's a direct contradiction with the assumption. Okay.
So why did you use the sharp selector?
So I use,
Right,
so in this trade-off right
Yeah,
here, right?
okay,
And
yeah.
we really need this 1 over T in order to pass it to this statement.
Because you take the unbound element.
Yeah, I
1
think
over
roughly,
T,
yeah, that's right. Yeah. Okay. Right, so if that was all fine, then allow me to now get to the exciting part. So I really wish to give at least some sense of the proof of the selector process conjecture and some hints at how you prove it for the sharp version. So allow me to do this here. So let me say that there are 3 results here, and we have the Kalai conjecture, kind of the high weight, uniform weight, high maximum regime. We have the Talagrand selector process conjecture, which is the regime where you want to get absolute constant lower bound on the maximum. And we have the sharp version of the Talagrand selector process conjecture. And roughly, well, in chronological order, this is where the idea was found, and then it can be applied here. But turns out that it is much easier and transparent for me to tell you now what is kind of the scheme behind the proof of the Kalai conjecture, which is fairly simple. And we'll see how to adapt that idea to this more complicated weighted setting, and then how to finally adapt that for this sharp version. And so roughly, the key idea is to use the so-called minimum fragment. In the Kalai conjecture, it looks very simple. In the selector process conjecture, it looks a lot more complicated. And here it becomes a tower of minimum fragments. And I hope I can tell you just a tiny bit about that at the end. But let me start by the proof of the Kalai conjecture. Not in full, or just the main ideas that are important. So roughly in the proof, in all of the proof, we will have 3 key components. There's a key definition, and then there's a key property, and finally we use that to deduce what will be the key lemma. So I'll write everything in this exact parallel. So I'll start in the Kalai conjecture with the key definition here. And let me write it in the following slightly suggestive form. So this definition works as follows. So given a subset W of X and a set H from our family script H, we will define its minimum fragment T, which depends on W and H at this point, as the minimal or minimum, when you can break tie in any way that you want, subset of H, such that if you look at the union of W and T, you get some set Z that satisfy what I will call a feasibility condition. So I write this way so that the parallel later will be more transparent. So I have W, I have an arbitrary set H from our family, and I want to find T. It's some minimal subset of H, so that together with W, T and W, the union of which is the set that we call set, will satisfy some condition that we want. So what's that condition? In this case, it's very simple. Z is feasible if Z satisfies the property that we want. Okay, so T is the smallest subset of H, so that the union of W and T lies in this property bracket H. So the union of W and T contains some other set from our family H. Okay, so let's observe that, well, we will try to apply this definition where W is a random set. If the random set already contains a set from H, if a random set is already feasible, anyway, we are done. We're happy. So let's assume that the random set is not feasible. So the key property that runs in all examples is this contrast between W and Z, right? I define this property of Z exactly so that it contrasts the property that W doesn't have, which is W is not feasible. And we'll see how this is useful. So that's the first definition. So now we come to the key property. And what does this key property say? It says that because of this contrast between Z and W, somehow it singles out the set T. The set T is very efficiently encoded once we are given information of the set Z. So given W, given W and H, given Z, which is the union of W and T, but I don't know inside Z where are the elements of T and where are the elements of W. For any set H hat in Z, such that H hat comes from our collection script H. So we will see later in the more complicated version of this, well, when Z is feasible, there's some witness for the feasibility of Z. So here Z is feasible if it contains some set H hat from the collection H. We'll call that H hat a witness for feasibility of Z. And here we're just saying for any, no matter how we choose the witness, H hat that proves that Z is feasible, we can identify T inside this witness H hat. And H hat is much smaller than Z. So effectively, this tells us that it is very easy to identify the set T. Okay, so once we have this key property one, anyway, this property is very easy to prove, right? So if I have here W, I have here T, and I have the set Z, but somehow you can find a witness H hat in Z which does not contain in entirety the set T, then of course I can just take as a new fragment this smaller set T prime, which contradicts the minimality of T. Okay, so this key property implies the key lemma, which I'll write in this way. So in the key lemma, we will construct a certain collection of sets. It will be the cover for some of the sets from our family H. So here, the cover C, which depends on W, is the collection of all sets T that arises as a minimum fragment TWH for some H. And we'll only look at those that have a large size. Okay, the conclusion is that the average, as we sample W according to XCP distribution of the cost of this cover this will have to be small. And we see exactly when it becomes small. It becomes small when T is some constant fraction of L. Okay, so I'll try to write out a proof of this key lemma. It's just one line, but roughly the key lemma in this setup tell us that large minimum fragments can be efficiently covered. So what we can do if we just iterate on the small minimum fragment, a logarithmic number of steps, and this will prove the Kalai conjecture. Not do the details, but it's kind of conceivable that we can do this iteration. So what's missing is I want to tell you about the one-line proof of the key lemma. Sketch maybe of proof of key lemma. So let's look at the quantity that we care about, this average over W of this cost or union bound proxy inside. So we can look at the left-hand side of the desired bound, and we can rewrite it in this form. So it's a sum over on W and T, for which T comes from this cover CW. We have the probability under the Bernoulli CP measure of W, and then we have P to the size of T. I claim that by the key property 1, this sum is dominated by the following one. So here, instead, I sum over all Z feasible. For every feasible Z, I make an arbitrary choice H hat that only depends on Z, and I will select here T, a subset of H hat of Z of size at least T. My claim, we have the same P to the T as before, and roughly Z is a set that is the union of W and a fragment of size T. So if you just compare between the probability under the CP measure of Z and the probability under the CP measure of W, you can bound this probability of W by the probability of Z dividing by CP to the difference in the size of Z and W. So the key property tells you that you can just sit down and check that every term that appears here, you can find here. So this is a genuine inequality. And now you are done. Okay, so the P to the T cancels. The number of ways that you can choose this T is, let's say, at most 2 to the L, because H hat has size at most L. And then you have the sum of this probability over Z, which is at most 1. So you have the cost of paying for T to 2 to the L. That's the complexity of this sum. And then you have C to the minus. Okay, so that's a very quick proof of the Kalai conjecture. So let's keep all of these boards above, and now we'll try to develop the parallel story for the selector process conjecture.
And I say that what you're erasing, what you've seen is special case of this, which actually motivated this proof, is the Rasdorf proof that you know, if you read a DNF, CDNF, I guess, with a random restriction, it becomes a TCNF.
Yes.
Just picking a random subset and having a random restriction is the same thing. H is just a DNF.
Yes.
But then, so that was the starting point of all this.
Yes, thank you, Arvi. Yeah, so of course, comes from the wonderful breakthrough on sunflowers by Alvarez, Lobet, Wu, and Zhang, and that in turn was crucially inspired, I guess, in part by Rasborov's switching lemma proof. Okay, so let's now come to the next hurdle. So in this case, we look at the selector process conjecture. So again, we sample W from this random distribution. And let's just recall what these guys are, this point. So this is maximization over H, lambda H of W. And well, let's assume that when we sample a random subset, we don't have that this maximum is large. If it's large, we already done. So this maximum, let's say it is small. Now, okay, maybe before getting to the specific, let me just say that the entire task is to build a parallel stories to that. The key is to define the correct definition. And in this definition, what do we need to design? We need to design the feasibility notion for Z, and pretty much that tells us what the minimum fragment has to be. And so what is the design principle for the notion, for the correct notion of feasibility? We'll stick to the same principle here. So feasibility of Z should allow us to contrast with this bad property of W star. So in particular, whatever notion of feasibility you define, you should at least guarantee that this maximum on Z is large. Okay. And the second thing that we will need to be able to succeed is for any H hat as before that explain the feasibility of Z, we will need to guarantee that we must be able to find the minimum fragment T inside a subset of H hat, let me call it F of H hat, it can only depend on H hat, and we will need that the size of T is at least some constant fraction of the size of this set, F of H hat. And you can see that if you can achieve these two conditions when you design your correct notion of feasibility, then you can run through the proof in pretty much the same way and get at the result. So, of course, there will be some challenges. So what are the challenges? Okay, maybe I just tell you the challenge in picture. So again, let me look at W that satisfies the bad property star, and let me look at already the set H hat that somehow witness the feasibility of Z, no matter how we define it. So roughly, it could look like the following. So let's say that we try to include enough information from T so that Z contains H hat in entirety. Okay, it could be the case that all of these elements in H hat have really small weight. So maybe let me draw it in a more suggestive form. So there are very few elements of H hat that lie outside of W here. So the cost of specifying these small set of elements, given this bigger set of elements, will be very high. But at the same time, all of these elements could have so small weight that there's no contradiction to the property that there cannot be a lot of weight lying inside W. So the first thing that we must do is we cannot just include H hat, the witness, in entirety into Z. We must ignore certain elements, and ideally we want to ignore elements with small weight. And the second challenge roughly looks like the following. So let's note that in the second principle in our design book, we need to guarantee that no matter what witness h hat that we use, we have to be able to find t inside a specific spot inside h hat. So you could think that maybe something sensible is the following. Maybe I just include enough information so that, for instance, I want to take t, which is all of the heavyweight element in h hat. But when I erase the boundary between w and t, I'm only given a set z, and I don't know which witness I used in order to come up with the set t. So might be that afterwards, there's some other set h tilde that is the witness for feasibility, and it's not clear that the elements here would still be the elements with large weight in h tilde, because the weight can change when you change the set. So it's the second tricky point. And to resolve all of these tricky points, you arrive at the following analog of the first definition. So let me just maybe write it, and I'll quickly explain it, but then very brief handway for the last hurdle. So again, we have the notion of feasibility, and we have the notion of the minimum fragment. So for W in X, H from our collection script H, we will consider, now there will be some additional parameter. Please, okay, so consider minimum B and minimum T such together with such that P H W H, again, it has to be a subset of H. This is our minimum fragment. It has size T, and it's satisfied that if we take Z, again, the union of W and T, then this guy is feasible. Of course, this means nothing so far. I have to tell you what feasible means. And feasibility, here, I will say it this way.
Where is B?
Right.
B feasible.
Thank you. Be feasible. In fact, let me, I will need here BT feasible. So Z is BT feasible if you have the following condition. There exists, again, I will call it a witness, H hat from script H, very familiar to us, such that we have the following condition. First thing is H hat B is a subset of Z. What is H hat B? We look at H hat, and let's order its element x1 up to xl according to the weight in H hat. And H hat B is just the top B weight element. Okay, so we demand that all of the B top weight elements from H hat, they have to be completely contained in this feasible set Z. And there's a slightly technical condition, so feel free to ignore it if it doesn't completely make sense. There exists W hat in Z of size Z minus T such that you have the following condition. Let's completely ignore this. I'll tell you more intuitively what happens here in a sec. Sum over I minimum lambda H hat X B lambda H hat Xi indicator Xi comes from W hat. This is at least 1/2 times the sum without the indicator. Okay. Maybe safely ignore it for a second. So roughly the second condition here is a condition that should at least guarantees that you can handle these kind of weight shifting situations. You know, maybe you take H hat and T consists of all of the heavyweight element in H hat, but now I look at another witness H tilde, and somehow T contains some low weight element of H tilde. In that case, you can check this condition to show that you can actually shrink the fragment a little bit in order to still guarantee that it satisfies all of the feasibility condition that we wrote down. So somehow this is a feasibility condition that you can make work. So you can see it's a lot more complicated than the situation we had for the Kalai conjecture. But with this definition, I don't think I have a lot of time left. You can push through to prove exact analog of the key property 1, so key property 2 and key lemma 2, and that proves the selector process conjecture. Let me say that our original notion of the fragment is, in fact, depending on your perspective, a little bit different. So we work under some dyadic discretization of the weights, and we define the feasibility condition a little bit differently. And there's a later work of Bednorz, Martinek, and Meller where they simplify part of the proof. In particular, they simplify this discretization, and kind of this notion of a fragment is closer to how they write the fragment in their paper. But it's useful for generalizing the fragment to the setting that works for the strongest result here, which is the sharp version of the selector process conjecture. And unless you are curious, I don't think I have time to tell you what happens there, apart from the fact that the minimum fragment is no longer enough. If the critical point that makes the definition of the fragment work in the case of the selector process conjecture is that, crucially, in the witness H hat, you have to ignore certain elements that you throw away. And these elements, they do not have to come from the set H. So maybe H looks like this, and H hat contains elements outside of H. This is a key point that makes it very different from the setup of the Kalai conjecture. So you may wish that once you prove the selector process conjecture, you can try to iterate it and prove the sharp version. So just iterate it S times instead of log times. But because you ignore certain elements of H hat that lie outside H, the iteration cannot work. And what happens for the proof of the sharp version of the selector process conjecture is you need to work with the notion that I call a tower of minimum fragment. And what happens here is roughly that you fold entirely the entire iteration into the notion of feasibility. And you fold all of that into the key property, and then that makes it work for the sharp selector process conjecture. I think cannot say a lot more than that. Allow me to spend just 1 minute on the epilogue, which is that this general proof strategy, we see here actually a very complex case of this proof strategy, but the general proof strategy works quite well. You see that all that we need to pay is we need to pay this complexity factor for selecting the minimum fragment inside its host, and we gain this factor of c to the minus t. We can use it in a variety of settings when you have additional assumptions to remove the log factor. So with Balog, Bernstein, Delcourt, and further, we prove that if you have, for example, additional VC dimension bound, then we can improve the log to an iterated log, to a log star. And there are various notions of smooth spread property and this integral strengthening under which we can remove the log factor. And all of that you can see very transparently just following the top 3 board here. So just following what we did for the proof of the Kalai conjecture. And I want to say that there is a lot more to do in this amazing picture of Talagrand. I really do wish to stay to climb through these hurdles, but there are also on the combinatorial side a lot of interesting connections. So we see some emerging connections with containers, with waiter client games, so some kind of positional games and so on. So yeah, I hope that was kind of an introduction that's interesting for you to this kind of direction. Thank you.
We have time for 1 or 2 questions.
One more. First, you say you impose the log L to a log star under bounded
VC.
VC?
Yeah.
Okay.
Yeah.
It's just the same. Integrality gap is just log star now for this bounded VC.
Right, that's right.
So that's a dual of the size of the.
So that's not even just applying to this integrality gap between the expectation threshold and the fractional expectation threshold. I can prove that this threshold, which upper bounds the fractional expectation threshold.
Fractional.
Yeah, so all of them are within this log star gap. for the bounded VC dimension case. And yeah, you can even see it if you just look at this proof. If you have additional VC condition assumption, then by, we know that if a set has bounded VC dimension, then the number of different intersections
Few sets.
yeah, there are few sets.
Polynomial,
They are polynomial instead of exponential, so that's the source of the improvement.
And you get anything from this sharp version for sunflower?
Uh-huh. Very good question. I have been thinking, but not yet. So I should say that, yeah, so there's the formulation that I mentioned at the end, the selector process conjecture, through duality, this fractional combination of sets being able to contain one of the target structure, that's almost, some of it seems quite close to what we want for sunflower, but there's difficulty in making it work.
You get the known result for the sunflower from this?
No, certainly, yeah, so already just from this proof, you immediately get the no result. If you wish, the correct constant, I believe what will be the optimal constant that you can put down. It's a clean proof for you to get the sunflower.
That was one.
It was two, but the rock star with the VC and the
VC.
sunflower.
Okay, so no more questions. Fine. Okay. Well, thank you very much.